In this video, we have the 1990 IMO problem 3. The problem requires finding all integers n is greater than 1 for which n squared divides 2 to the power of n plus 1. So the first step to approach this problem is to find the smallest prime factor of n. You can let p be the smallest prime divisor of n. Then why do we do this? Well, we're going to use the property divisors. We just let p be the smallest prime divisor of n. Then, since n squared is a factor of 2 to the power of n plus 1, it follows that p is a factor of 2 to the power of n plus 1. This can be written as a congruence. Two to the power of n is congruent to -1 mod p. Now, if you're wondering where this -1 came from, well, we know that 2 to the power of n plus 1, since it's a multiple of p, that will mean that it's going to be mod 0, or the remainder when divided by p is 0. So 2 to the power of n, which is 2 to the power of n plus 1 minus 1, is going to be congruent to -1 mod p. Then we can square both sides, so we'll have 2 to the power of 2n congruent to 1 mod p. By Fermat's little theorem, we know that two to the power of p minus 1 is congruent to 1 mod p. Note that p cannot be 2 because 2 to the power of n plus 1 is odd, so n squared and n must be odd, meaning all prime factors of n are odd. So we can let d be the order of 2 modulo p. From the congruences above, d must divide both 2n and p minus 1. Therefore, d must divide the greatest common divisor. Basically, we'll have let d be a factor of the GCD of 2n and p minus 1. By definition, p is the smallest prime factor of n, so any prime factor of p minus 1 is strictly smaller than p. Therefore, n and p minus 1 can share no common prime factors, which means that the GCD of two and p minus 1 is equal to 2. This implies that d equals to 1 or 2. And here, we can ignore the n, because n is just the factor of multiplicity. So in reality, just d is the factor of GCD of 2 and p minus 1. Now we can plug in these two values. If d equals to 1, 2 to the power of 1 is congruent to 1 mod p, which means that p divides 1, an impossibility. If d equals to 2, 2 squared is congruent to 1 mod p, which means that p divides 3. Since p is prime, we'll have p equals to 3. Now we must show that n must be a power of 3. We have shown that n must be divisible by 3. Let's assume that n has another prime factor q. Based on step 1, q must be a greater than 3. Then same logic will apply to q. So the order of 2 modulo q, let's call it d prime, must divide GCD 2n q minus 1. So we let d prime divide the GCD of 2n q minus 1. The prime factors of n are 3, q. The prime factors of q minus 1 are all smaller than q. The only prime factor n and q minus 1 could share is 3. Thus, the GCD of n and q minus 1 must be some power of 3. Let's call it 3 to the power of k. This leads to d prime dividing 2 times 3 to the power of k for some k. From 2 to the power of n is congruent to negative 1 mod q. We know the order d prime cannot be 1 or 2 as q is greater than 3. This creates a contradiction showing that n cannot have any prime factors other than 3. Therefore, we'll have n must be a power of 3. So we let n equals to 3 to the power of k. K we can say is greater than or equal to 1. Now I'm going to find a specific value of n. The condition n squared is divides 2 to the power of n plus 1 becomes 3 to the power of k squared is divides 2 to the power of 3 to the power of k plus 1. Using the lifting the exponent lemma, for a prime p greater than 2, the lemma states that Vp times a to the power of n plus b to the power of n goes to Vp a plus b plus Vpn if p divides a plus b and p does not divide n. A more general form of our case is going to be basically v3 2 to the power of 3 to the power of k plus 1. This equals to v3 2 plus 1 plus v3 3 to the power of k. Here, v3 is the exponent of the highest power of 3 that divides x. So we'll have v3 times 2 to the power of 3 to the power of k plus 1 equals to v3 times 3 plus v3 times 3 to the power of k. This just equals to 1 plus k. Our condition that 3 to the power of 2k divides 2 to the power of 3k plus 1 means that the power of 3 dividing 2 to the power of 3k plus 1 must be at least 2k. So we'll have v3 2 to the power of 3 to the power of k plus 1 greater than or equal to 2k. So 1 is greater than or equal to k. Since n is greater than 1, we must have k greater than or equal to 1. So this means that k equals to 1. Then, therefore, we'll have n equals to 3 to the power of 1 equals to 3. And that will be the only solution to this problem. We can check our solution. For n equals to 3, 2 cubed plus 1 divides 3 to the power of 2 equals to 9 to the power of 9 equals to 1, which is our integer. So the answer to this problem is just going to be n equals to 3.